Hello everyone. We are going to see one important aspect in power electronics, how to design inner voltage and current control based upon our desired performance and bandwidth. So we have given filter parameters, converted side parasitic resistance as Ri, converted side filter inductance as Li, damping resistance as Rd, damping resistance Rd, filter capacitance Cf, grid side parasitic resistance as RL, and grid side filter inductance as LL. So first we have voltage controller, and this voltage controller regulates the voltage over the capacitor and the damping resistance that we denote as VC. So damping resistance is not large compared to the reactance of the filter capacitor as 50 Hz. So B, so just B, uh, VC is used as voltage drop over the capacitor, and we neglect the voltage drop over the damping resistance. To simplify the control structure, regulation is performed in the synchronous reference frame DQ axis. This is obtained by deriving the governing equation traditional ABC frame and subsequently using the transformations. So we apply KCL on the single phase equivalent of the LCL filter. We provide this inverter current that is equal to this load current or grid current and this current through these filter capacitors. In the alpha beta frame, that is a stationary reference frame, the equation remains the same for the single phase equivalent, and using the alpha beta to DQ transformation, we will get this separate axis in the separate equation in the DQ axis. So now transforming this equation in the frequency domain, we will get this equation that is denoted as 3. And the equation in the above equation, we can see there is coupling term present, and that is omega CF VCQ for D axis voltage and minus omega CF VCD for the Q axis voltage. And also there is coupling between the voltage and the currents are present. To improve the dynamic response, the decoupling measures are taken by removing these components with a feed forward term in the controller. Now we assume this uh, now we assume this current through capacitor as ICD and ICQ, and we can rewrite the equation 2 with the help of this equation 4. Now we take ICD and ICQ as the equivalent control variables. Their values can be determined using a PI controller, which is given by this equation 5. The output of the voltage controller is the current reference for the current controller to provide the reference current. The relation in equation 4 is used along with a PI controller of the corresponding voltage, and using the above relation we get this reference current that is coming from the output of the voltage controller. This enables the voltage to be adjusted by PI controller according to the following open loop transfer function, where we assume perfect decoupling. And here this KPV and KIV are the proportional integral gains of the PI voltage controller. And after the decoupling, this transfer function is valid for both the D and Q axis voltages. And the tuning which is present in the next session is because of this equal in both cases. So we are doing the same tuning for both D and Q axis voltages. Now, how we tune the voltage controllers? We have used the pole placement method. It compares second order characteristic polynomial with the closed loop transfer function of the system that is tuned. The system that is controlled by the PI controller is 1 upon SCF. To obtain gain parameters, the second order characteristic polynomial is used S square 2 psi omega ns plus omega n square, where psi is damping ratio of system and omega n is natural frequency. The closed loop transfer function for the voltage controller follow this equation. So we got the closed loop transfer function and we have characteristic equation. So we compare this based upon desired performance and bandwidth. So we have to get a well damped system, this damping coefficient is set to psi equal to 1.1, and now the natural frequency of the voltage controller should be sufficiently high to give a fast response in the voltage control. It should not be so high that it alters the fast current control, and therefore to ensure sufficient bandwidth between controllers, it is set a decade lower than the natural frequency of current controller. So we have switching frequency of 15 kilohertz, and then we have this frequency for the current controller as 1 decade lower. So we got 3000 pi. So we get the frequency for this voltage controller as 300 pi. Now we will substitute all these values, and we have given this filter capacitor value. We get these parameters for PI controller in the voltage controller. Now we can verify this voltage controller tuning by plotting this Bode plot. So we have this upon plotting the Bode plot of open loop transfer function, we get the gain margin as infinity and phase margin as 78.55 degree and phase crop frequency as 2115. 78.76 radian second. So the gain margin infinite and phase margin in this much 78.55 degrees. So these are well within the rules of having 6 dB gain margin and 45-degree phase margin. Now let us come to the current controller. The current control regulates the current out of the inverter, that is denoted as II. This control should be faster than the voltage controller to ensure decoupling between the controllers. In the same way as with the voltage control, we have transformed this into DQ reference frame, and using KVL on single phase equivalent of circuit gives the inverter voltage as this much, and in alpha beta from this equation remains the same, and using the alpha beta DQ transformation we get this equation that is denoted by 15 for the DQ axis. Now we can transform frequency domain, and upon rearranging we will get this equivalent equation that is known as 16. In equation 16 there became see again there is coupling between the two axes by the parts given as omega Li IIQ for the D current and minus omega Li IID for the Q current. Additionally, there is coupling term between the currents and the voltages. The coupling measures are therefore utilized by removing these components with a feed forward term in the controller. So now for the given circuit configuration, considering this much, this voltage drop across the filter, across the inverter side filter inductance VFD and VFQ in the separate axes. So we can write again this equation in this way, 15 can be written in this way. So by taking VFD and VFQ, the equivalent control variables, their values can be obtained using PI controller by given by this equation 18. The output of the current controller is the voltage reference for the inverter. To provide the reference voltage in the relation equation 17 is used along with the PI controller for the of the corresponding current, and we get the final reference in the DQ reference frame for the PWM generator, or you can say the modulating signal. So upon neglecting the resistance term, we will get this final reference voltages for the inverter in DQ reference frame. This enables the current to be adjusted by PI regulator according to flowing loop open loop transfer function, and combining this references of 20 and assume binary condition that is zero axis voltage 0. So gives through the inverse Clark transformation. Here we have used the inverse Clark transformation, and the reference voltage in ABC coordinates got as V reference, and this reference is used by PWM generator to create on-off signals for the inverter switches. So the system that is controlled by PI controller is this much, and the closed loop transfer function for the current controller follows from the equation 21 is this much. Now we compare this closed loop transfer function with the characteristic equation. So we will get KPC and KIC. Characteristic equation is what is that? S square plus 2 zeta omega ns plus omega n square. So psi is taken as 1.1. Now we have omega ni as 3000 pi radian per second. So we will get the resulting KPC controller gain for the current controller as this much, KPC 10.536 and KIC 45,141.6. Now again we will verify the controller design using the Bode plot. So we have made the Bode diagram for the open loop transfer function, and we get again margin is infinite and phase margin is 78.55 degree, phase crossover frequency 21,157.3 radian per second. So we can notice that crossover frequency is at desired 10 times higher for the current controller than the voltage controller. So this, as previously presented, the margins state that this is stable solution. So that's all. Thank you. If you have any query, you can ask in the comment box. Thank you all.